I'm going to be explaining the idea of overflow. The idea of overflow is the result of the arithmetic should fit in the number of bits of the operands. So here are two important things you must know. The arithmetic is correct, and overflow means your result does not fit in n bits. So that's the idea of overflow. The result of the arithmetic should fit in the number of bits of the operands. Here is an unsigned example using n equals 2 bits and the color-coded range of numbers that n number of bits can represent. And so this example exhibits overflow. And it's important to remember, your arithmetic is correct. Overflow means your result does not fit in n bits. So we have binary 3 and 3. You add 3 and 3 and you get 6 in binary. And you have overflow because 6 in binary does not fit in the number of n bits that you used. You used 2 bits in your operators and your result uses 3 bits. So there's overflow. And here's a signed example of overflow using n equals 3 bits. This is -4 and -1. And you add them and you get -5 in binary. And the arithmetic is correct, but you have overflow. The result of the arithmetic should fit in the number of bits of the operands, 3 bits for each operand. The result should fit in 3 bits, but it doesn't, it's in 4 bits, and overflow means your result does not fit in n bits. How to determine overflow? You can use the range, and that works for both unsigned and signed. You can just check your result, check the range, and you'll know if you have overflow. Now if you're working with signed numbers, there's another way to check for overflow, and I'm going to tell you now. So, check if you have a different carrying value going into the most significant bit and out of the most significant bit. Okay, and I'll explain that using the signed example. So, the carrying value going into the most significant bit would be 0 and 1. There's no carrying, it'll be 0. Now, 1 and 1 will produce a carry out of the most significant bit of 1. And so that's how you know you have overflow. You have a different carrying value going into the most significant bit and out of the most significant bit. And using this method, you can implement this into circuits when you're working with logic gates. If you perform binary arithmetic and you end up with an extra bit, in all cases ignore the extra bit. For example here, in this signed example, you do get an extra bit, and what do? Ignore the extra bit. In this example, -1 and -1 add to -2, and that does fit in the range of a 3-bit binary number. And so, ignore that last bit. Now, signed extension is how you convert an n-bit binary number into any number of bits and maintain that value for your binary number. So, if you're working with an unsigned binary number and you want to extend it to a 6-bit number, then you just add 3 zeros. Now, if you're working with a signed -1 and you want to convert that into a 6-bit -1, then you just extend the sign. You add 3 ones. So, if this was a +1 and you wanted to convert that into a 6-bit +1, then you just add 3 zeros.